The pH of the body is tightly regulated. When it increases, for example, by an increase in bicarbonate, the carbon dioxide also increases to pull the pH back to normal. But how do we know that the increase in carbon dioxide is part of the compensation and not a disorder in itself? If the carbon dioxide keeps on rising so much that it has now decreased the pH, is it still compensation? Or is it a different disorder? To know that, we must know one thing, that is, how much compensation is expected. And that is why we have equations to predict compensation. And today we'll learn how to use them. To understand what equation to use, we need to know the primary process first. Is it metabolic acidosis, metabolic alkalosis, respiratory acidosis, or respiratory alkalosis? And from our previous videos, we know how to understand which is the primary process for any given ABG. If you haven't watched those videos, watch them first and then come back to this. Okay, let's start with metabolic acidosis. Here the pH falls because of a fall in bicarb, and as a result, lungs exhale more carbon dioxide and get rid of it. Now, to know how much carbon dioxide gets washed out for a given amount of metabolic acidosis, researchers plotted it out on a graph. They put the PCO2 on the vertical axis and bicarb on the horizontal axis. And they found that there's mostly a linear relationship between the two, as depicted by this line which cuts the axis at about 8. Which means theoretically, if your bicarbonate falls to 0, your PCO2 will still be around 8. And that's as low as it gets. So when we derive the linear equation from this graph, we get this. To simplify, the expected PCO2 will be 1.5 times the bicarb because of the slope of the graph. To this we add 8 because it doesn't get any lower than that. Also, to account for variation between individuals, we keep a range of plus or minus 2. And there you have it. We derived what is called the Winter's formula. So every time you see a metabolic acidosis, you should apply this formula and see if the PCO2 falls within the expected range. If it does, fine. If it doesn't, you're looking at a mixed disorder. Let's move on to alkalosis. Can we apply the same formula here? See, here the primary problem is a rise in bicarb, in response to which the body is slowing down the ventilation and retaining more carbon dioxide. But hypoventilation has a limit. You can't just keep storing carbon dioxide. So here the compensation is weaker. You can simply remember that for every single unit rise in bicarb, the CO2 rises by 0.7 only. And that's all you need to apply when you see a metabolic alkalosis. Now let's see how respiratory acidosis is different. Here the primary problem is retention of carbon dioxide, so the bicarb has to rise. Now look at what happens in the blood. Carbon dioxide combines with water to form carbonic acid, which isn't very stable, so this reaction is in equilibrium in both directions. Also, carbonic acid can break into H+ and bicarb ions. When carbon dioxide rises, it can push this equilibrium to the right. So now, more free H+ ions will be available. But CO2 can vary within minutes to hours. And if all this extra H+ ion gets released, it can cause severe acidosis. To prevent that, we have a lot of absorbers present in our blood that can bind to this extra H+. Some of these are hemoglobin, phosphate, and proteins. We call them chemical buffers. These are your frontline warriors for any change in pH. When this happens, the bicarb generated as a result will cause an increase in pH to compensate. Obviously, this mechanism isn't much efficient. So for every 10 mm mercury rise in PCO2, the bicarb increases only by 1. Also, this happens for a case where the respiratory acidosis is acute. But when this process has been going for a while, which is chronic respiratory acidosis, the game changes, because now the kidneys have to step in. Now they can change the equilibrium by increasing the excretion of the extra acid and can also regenerate bicarbonate. This process in a working renal system is much more efficient. So now for every 10 mm mercury rise in PCO2, the bicarb can now increase by up to 4. Similarly, when we look at acute respiratory alkalosis, here the direction of the equilibrium is shifted to left because CO2 is being washed away. This will result in a decrease in H+ ions and increase in pH. To counter that, again we have the same chemical buffers. But they can release H+ ions more readily than they can absorb them. So for every 10 mm mercury fall in PCO2, the bicarb decreases by 2, which is twice the compensation that these buffers could provide during acute respiratory acidosis. Finally, when this process also becomes chronic, the kidneys can again step in and compensate in the reverse direction by decreasing the acid excretion and increasing the bicarbonate excretion. Now since kidneys are very efficient either way, here also for every 10 mm mercury fall in PCO2, the bicarb decreases by 4. Now here's the summary. For chronic respiratory problems, the compensation is 4:10 because chronic means that kidneys have entered, and kidneys are much more efficient. But for acute, the compensation relies mainly on chemical buffers, which are more efficient at decreasing bicarb. So there we have a ratio of 2:10, but for increasing bicarb, they can only manage up to 1:10. So now you understand that for every disorder, you can apply the formula to rule out if there is an mixed disorder. Now suppose you handed this ABG. Don't look at all the values at once. We'll see it one by one. The pH is 7.28, the bicarb is 12, and the PCO2 is 26. Easy, right? So we know from the pH that this is acidosis. Also, since carbon dioxide is washed out from 40 to 26, so this is respiratory alkalosis. And the bicarb has decreased from 22 to 12, so this is metabolic acidosis. Now from this, which process is the primary? Of course, metabolic acidosis. Now we know that for metabolic acidosis, we have the Ventus formula. From that, we get that the expected PCO2 will be 1.5 times the bicarb value plus 8 plus or minus 2. So let's put in the values. 12 into 1.5 plus 8 plus or minus 2. This becomes 18 plus 8 plus or minus 2, which gets us a range of 24 to 28. And our actual CO2 is sitting exactly in the middle of the range. So perfect compensation, right? But then why is there still acidosis? You see, this is what happens when there are multiple processes at play. We'll find out in the next video. Till then, like, share and subscribe to Renal Dose, and comment if you want to see a video on any other topic. Thanks for watching.